problem that presents us. We have Bob walks to Alice's house 5 blocks west and 2 blocks north. And what we'd like to do now is to simply see what this motion looks like. And when we take this motion here, it makes sense to put our origin at Bob's starting location. So we have a reference frame with a positive x-axis and a positive y-axis that is going to represent east and is going to represent north. And so if Bob walks 5 blocks west, then the first part of his motion looks just like this. And then if he walks 2 blocks north, the second part of his motion is going to look just like this. And so there is Alice's house. Now here's the thing. Assuming that there are not buildings in the way, Bob actually wasted a little bit of effort. What could he have done instead? He could have gone straight there. And if he went straight there, like this, then what would be the same and what would be different about the blue motion versus the red motion?
The red motion takes us down.
Same or different?
Yeah,
The distance that he travels would be different. What would be the same?
destination.
The destination and the origin, right? So we would say that the change in his position would be exactly the same, the final position minus the initial position. And we're going to represent that change in position for delta x. Now we're going to represent it with a pair of numbers, one for the x direction and one for the y direction. We're going to say that the change in the position was minus 5 in the x direction and positive 2 in the y direction, and the units are blocks. And this pair of numbers right here that represents his change in position, we're going to call a vector that points 5 to the left and 2 up. So Sean and then Matt. Go ahead.
Your little triangle, like half triangle piece in front of the 5 and after the 2.
Yes. So these angle brackets here are going to be the symbols that we use to indicate that we have a vector quantity. And they're obviously pretty closely related to the parentheses we use for points, right? And so the difference is that a point is going to refer to a location. You are here. And a vector is going to be something that has direction to it that would get me from the origin to the point following it, negative 5 coming to it.
Is it always going to be like this?
Yes, angle brackets. And these angle brackets give us a vector with x and y. Here's our word components. The x component is going to be the amount of change in position in the x direction. And the y component is going to be the amount of change in position in the y direction. Matt? Same question. Good. So if Bob now walks to Charlie's house with a second displacement, let's make up some numbers. How about 6, 4? Yeah. Blocks. Then this displacement means starting at his current location at Alice's house, he is now going to walk 6 blocks in which direction? East. And 4 blocks in which direction? North. And so now he is over 6 and up 4, which puts him here at Charlie's house. And the interesting thing about this is it doesn't matter whether he walked across and up or straight there, his displacement is the same. Let's just go ahead and just draw his displacement vector. And this displacement vector is 1, 2, 3, 4, 5, 6, to the right, and 1, 2, 3, 4 up. How are we doing so far? Does this make sense?
Yeah.
So just distance is different, but displacement is the same.
That's right. For the blue path and for the red path, the distance walked is different. This guy is going to be 5 plus 2 is 7. This guy is going to be done really with Pythagorean theorem. Right? Square root of 25 plus 4 square root of 21. And the same thing is true here. If he walks over and then up along the black path, then his distance would be 10. But his displacement, his distance along the green path, would be the square root of 36 plus 16. Good. Okay, so far so good. So, we're going to call this object right here a vector object. And I'll give you a definition in just a minute and tie that in with this. But for now, we're going to think of this form in which we are putting this vector object in rectangular form. And by rectangular, what I mean is that I am giving you its components in terms of perpendicular axes, over and up.
So that whole term is the vector.
Yes, the whole object together is the vector. This amount over, that amount up. Okay. Now, earlier I mentioned that vectors have magnitude and direction. In fact, that's one way that physicists define vector quantities. So what does that mean to say that this vector here has magnitude and direction? The magnitude of a vector is going to be its length or its size. In other words, the magnitude is the distance from here to here. And you might think that it would be hard to find the magnitude of the vector, but actually it's not. We're going to use absolute value bars to represent the magnitude of a vector. These absolute value bars are really pronounced magnitude of or size of. So the magnitude of delta x is going to be its length or size. Its magnitude.
Magnitude equals delta x?
No, no.
Or absolute value of delta x?
That.
Okay.
What's the delta x above that?
The delta x is the vector object, this arrow that has the size of delta x in the absolute value bars is going to be its magnitude. It's just going to be a number. It tells you how long it is. So let's see if we can figure out that size. If we go back to where are we? Yes, if we go back to the first delta x that we had, that took us from Bob's house to Alice's house, that vector had components of -5, 2. The magnitude of that vector was the length or the size right here. And I want you to observe something. When you look at the -5 in the x direction and the +2 in the y direction, and the overall delta x that I drew right there, what shape do you observe this as? What kind of triangle?
Triangle.
And does it always have to be a right triangle?
Does it always have to be?
Yeah.
Maybe, yeah.
Yes, because it's always over and up. Very good. Yes, that's exactly right. Because I'm giving you this in rectangular form, the angle between the components will always be a 90-degree angle, and you always form a right triangle. Hey, we like right triangles because whose theorem always applies to right triangles? Pythagoras' theorem. That's right. So that the magnitude of our first delta x is going to be equal to the square root of the x component squared plus the y component squared, or the square root of 25 plus 4, or the square root of 29, which on our calculators turns out to be 5.2-ish, something like that. Oh gosh. Well, I get it. 5.4. Okay. What units would that be? Well, the magnitude is the length of this thing, and what is the scale that I'm using? Am I blocks? That's right. So this would be 5.4 blocks. All right. I'd like for you guys to all find the magnitude of x2, delta x2. Go. Sure. Yeah.
Which line was delta x? Is it the green line?
Yes,
Okay.
exactly. Delta x2 was 6, 4. And what do you get for that? And units? Notice that a vector and its magnitude always have the same units, because you are taking units and squaring them, and then taking the square root of that result. That's good. Anybody get anything other than 7.2? Okay? 2 newbie mistakes I want you to avoid. Newbie mistake number 1, notice that when I square a negative component like -5, I've got to get a positive number. So that when I compute magnitudes, I actually just ignore these negative signs, and I do it directly as square root of 5 squared plus 2 squared, so that I don't accidentally subtract. That's the first thing. Yes?
So what is the absolute value for if it's automatic from the positive versus?
So this is not actually, I'm using the same signs as absolute value signs, but it doesn't actually mean absolute value, it really means magnitude. And the relationship between those two notations is this. We have been using acceleration and displacement and velocity as vector quantities, but I didn't talk about vectors. What did we use for in motion in one direction? What did we use to indicate our direction? Positive and negative signs, right? But if I needed to know something like speed, which is the magnitude of the velocity, then I would take the absolute value, and what did that give you? It gave you the size of the velocity without its direction. So the connection here is that absolute value for real numbers gives you the size of that number. So this is a more general way of thinking about size. We're going to pronounce it magnitude of. Yeah. So delta x here is a vector quantity. Its magnitude is the opposite of vector is a scalar. It has a magnitude form. Yep. Good. Any other questions about that? So to summarize everything that we've done here comes our formula. If I have a vector A, we're going to do it like this. We're going to do a whole lot with generalized vectors, and we're going to write, if I have a vector A, I'm going to write it with angle brackets. AX is going to be the x component, the amount over, and AY is going to be the y component, the amount up, like this. If I need to be clear that A is a vector quantity, sometimes I'll put a little vector hat over it like this. And that half arrow vector hat means A is a vector quantity. It's just for emphasis.
Wait, Tom, excuse me, can you repeat that, what that, little, half triangle thing is? Oh, not half triangle, but the little, yeah, there.
The angle brackets?
Half arrow.
Yeah,
Yeah.
that.
I call it a vector hat. It just tells you that A is a vector quantity.
Oh,
So if I have vector A, which is AX over and AY up, and these two together combine to give me A, this is the picture that we would draw for that vector quantity. We have a horizontal component and a vertical component that combine to give me the overall vector. That make sense? And now if I want to know its magnitude, then it's Pythagorean theorem every time. The square root of the x component squared plus the y component squared. So you can think of this as our first formula for the day. And it's just Pythagorean theorem.
but why do you use all these A's? Like, why can't you just, like, keep it, like simple? Is this more simple?
Well, it's generalizing.
Oh, just an example.
I need to, it's actually a little more than an example. It's taking what we did there with Alice, Bob, and Charlie, and it's saying, in general, for any vector quantity, this will give you the magnitude.
Gotcha.
That's a good question.
That's the fine magnitude, right?
That's the fine magnitude. Now, in addition to having magnitude, vectors also have direction. I want you to think about this for a minute. Suppose I tell you, Bob starts at his house and he walks 5 miles. Where is he?
5 miles from the starting point.
He's 5 miles from the starting point, but you can't give me a unique place, right? Because I didn't tell you what direction. Now, what if I told you he starts at his house and he walks 5 miles northwest? Now you have a direction. And that direction is going to be northwest from his original house. So how do we want to specify our direction? The way that we're going to specify our direction is by use of a direction angle. So if I have, this is our vector A right here, and I can measure its magnitude either with Pythagorean theorem, or honestly, I can bust out a ruler and measure it directly. So if this is my ruler right here, and let me adjust the ruler a little bit so the scale is correct. See how my ruler's scale doesn't line up very well? Let me make that happen. Yes. That's here, this is right.
Wait, but the numbers are moving with it.
Yes, exactly. So what I'm doing is I'm rescaling my ruler so that it fits the graphic. Here we go.
So that's not really 10 centimeters, is it?
Now, I've got it so that each 2 squares corresponds to 1 centimeter. See? Yes.
But you don't, but like, how do you know? That's just for this thing that you're explaining. Right?
Yes. Right.
Because in real life, like, this would.
Oh, yeah. So if I actually got out a centimeter meter stick, these aren't going to be really centimeters.
Right.
I can do that if you want. It's right
No,
here.
I was just asking for, like, future.
No, I've always been curious here. So these centimeters right here that you see are actually about 3 centimeters in real life. And it's just sort of amplified so you can see it. Yep. So a ruler is a great way to measure the magnitude of my vector, because now I can put that ruler at the tail of the vector. We call this the tail. And then I can put the ruler along the vector and measure all the way out to the ruler's, to the vector's head. And the vector's head comes out to 3.60 centimeters. And so that's not so bad. With a real ruler, it's easy. So we would measure the magnitude of A as 3.60 centimeters, just like that. We would get the same result if we could do perfect measurements and measure just the components. So my component of A in the y direction is 2.7. And my component of A in the x direction here is going to be 2.5. So we would say that A itself, the vector A, is 2.5 over and 2.7 up. And we would say that the magnitude of A is 3.60 centimeters. And sure enough, and I just made this up, but I'm so confident in the math that I'm convinced that when I do the magnitude here, I'm going to get 3.60 plus or minus a little bit because of rounding, right? So let's see that happen. And 2.5 squared plus, 2.5 squared plus 2.7 squared square root, and I get 3.68.
Close.
Boy.
It's
So inaccurate.
The system doesn't work.
No, the system works just fine. What's that? Hey, you're right. Thank you. That's right. Does that change my computation here? That is going to change my direction, isn't it? That's a good catch. Thank you. That's right. So my A here has a negative x component, and so I needed to include that negative sign in my x component, not the y component, which is still up. Okay? Now, what about that direction? The direction we're going to specify with a direction angle. And the direction angle we can measure directly with a protractor, and we're going to measure it from due east always. The direction angle is measured counterclockwise, CCW counterclockwise, from due east. What I mean by that is, I'm going to put the 0 degrees along the positive x-axis, this way, so that 0 is always here at due east. And then I'm going to measure positive angles in this direction. Does that make sense?
Can you say that one more time? It's better to read that.
Due east is going to be 0 degrees, always, and positive is going to be counterclockwise, like that. So if you put the origin of your protractor right at the origin, and you at the tail of your vector, I should say. And if you orient your protractor so that 0 is due east, then naturally the direction of your vector pops up, and it is the direction that you get from due east. There, that's what I was looking for. This angle right here, which is 131 degrees. Not the 50 degrees. The 50 degrees is measured from west. In fact, let's
So when if a question asks you like to measure from due west, you do the other way.
your question should not ask you to measure from due west. We're going to take 0 degrees to due east.
Okay.
See? Yeah.
Okay.
Due east means you're starting at 0 and going.
And going this way. That's right. Which is why I got 131 and not 50. The angle that I'm measuring here is the angle from due east.
What's CCW?
Counterclockwise. The directions of the counterclocks go. Nobody laughs.
Oh, terrible. I'm sorry.
Okay. Now, if I want to represent my vector, then in terms of its magnitude and direction, then the form that I'm going to use is, we're going to call that the polar form. And since I have A right here already in rectangular form, then we can also represent A in polar form, and it's going to go like this. We're going to put the magnitude first, or 3.6. I'm going to use the one I computed, 3.68. Let's do 3.60. You measure it. That's data. 3.60. And I'm going to use an angle sign to indicate its direction, which is 131 degrees. And I'll put the units after the vector in both cases.
Is that the angle sign?
That is an angle sign. And the symbols that your book uses for the magnitude, well, it's going to be the magnitude of A, and the angle, we're typically going to use the Greek letter theta to represent the angle. Okay. Notice that we have something really interesting. We have two different ways to represent the same motion. I can tell you how far over and how far up, and that's in rectangular form. And that is equivalent also to telling you how far out at what angle. And those two forms or ways of thinking about it are complementary forms for the same vector object. The vector object is literally the arrow that I drew. That's A. And then my representation of A can be either in terms of its horizontal and vertical components, x and y components, or in terms of its magnitude and its direction. So we have these two different representations, and tomorrow we'll nail down how to take one representation and turn it into the other. But for today, I just want you to see that we've got these two representations, and I can measure both of them with a ruler and a protractor if I need to. And tonight you're going to be doing something.
Now that's multiplying the magnitude of A by the angle, right? Or is that a less than?
No, none of the above. So there's no multiplication happening here.
Okay.
All that we're doing is we're saying A is the magnitude at a certain angle.
Okay, so that's not like an operation, it's just.
That's not an operation, it's just specifying the information.
Gotcha.
It's interesting that you mentioned that because way the heck far in the future, when you take like complex analysis as a junior in college, then there's going to be a kind of multiplication involved here with complex explanations. I didn't say that. Yes. Yeah. Let's do like a practice run, because we've got 7 minutes. So let's actually see how this all works out. Okay. Does anybody have a protractor with them?
Yeah.
Okay. If you've got a protractor, great. If not, bring one tomorrow. I've got some spare protractors, so I can distribute them and let you share. And also,
Well, it's up here is going
share with them.
That's good. That's what I said.
All right.
Sorry.
Look at those trees shaking.
That would be, yeah, you
If
should
you've
know
got some,
more than just physics. It's good physics.
if you've got some graph paper, that would be great. If not, you can use regular old paper.
Does anyone need graph paper? Does anyone need graph
Give
paper?
yourself some nice straight coordinate axes with your ruler.
Oh, there's the just.
And I'd like for you to draw up for yourself a vector A. You can draw it with any magnitude and direction you wish. And now do the following things. First of all, find the magnitude of A with your ruler and the direction of A with your protractor.
So we can do whatever,
Yeah. Now, Josh tried to draw a vector like this. There's two things wrong with this. Yeah, what's the direction of our vector? Is it? Maybe it's down.
I don't know where that's going.
I don't know where that's going either. What's it missing? This is a vector with two tails and no head.
Origin, reorigin. Come on.
There you go. That fixes it. Now, here's the other thing that might disturb you. Is this vector legitimate given that it's not starting at the origin? Yes. Vectors can move around, and as long as they represent the same amount, as long as they have the same magnitude and direction, they are the same vector. So these two vectors are both A because they have the same over and the same up. Vectors with the same direction we call parallel vectors. If they are in the opposite direction, we call them anti-parallel. Okay.
Or,
This,
Yeah.
its name is theta. Please do not call it theta, which is kind of cheese. It is theta, it is the Greek letter TH, but we use it for angles.
I'm gonna take
Is this kind
No, I'm so blunt about everything I
Yeah,
said.
it says give me an angle sign. That angle sign was saying add that one. Yes, sir. Yeah.
Okay.
Yeah.
there is no set.
Okay. According to my ruler, this is 4.2. At an angle of at an angle of 27 degrees. And so the measurement of it is really pretty simple. Did you all find that your measurement was pretty simple?
Yeah.
Did you remember to measure counterclockwise from due east? Okay, good. Just a quick check.
This is
No.
For this vector B, my angle will be between what value and what value? My angle will be greater than 180 and less than 360, less than 270. Yeah. So 180 is here, 270, which is also less than 360.
Wait, so if in the B,
Yeah.
the B place, right?
Yeah.
Are they gonna ask from due north?
No, from due east always.
Oh, it's from due, okay.
I am measuring all the way around to this angle. Now, here's the thing. Most of your protractors are only 180-degree protractors, right? So how do you deal with that?
Oh, you just gotta flip it upside down.
You're going to flip it upside down, and you have to remember to add your 180 as you go around. Yeah. So you may have to be a little clever with your measuring devices. My measuring device is cool because I get two sides. I go one. So this angle right here comes out at 252 degrees, which as advertised is the 22. Yeah.
Are they always gonna ask counterclockwise?
Always counterclockwise, always from due east.
Alright. Because I don't like these tricks and games. Like,
No tricks, no games.
Yes.
Always counterclockwise, always due east. If they are, some of the problems in the book actually do say such and such an angle from due west or such and such an angle from north. So you have to figure that out. But that doesn't mean that we're going to change our standard. It just means that that's the information that comes. Okay? Yes. Well, if you put this here, put this in. You put this here, and your angle comes up to 66 plus. Yep. All right. Now here's the next thing I want you to do before the bell rings. Having found A in our polar form, kind of messy here.
Why is that called the polar form? Does it matter?
Why is it called polar form?
Yeah.
Because it's expressing this in terms of the angle from the polar axis.
Okay, that's
Yep. Now I'm going to come back and ask, what is this in rectangular form? What are its x and y components? So use a ruler to estimate the x and y components of your vector x. No computation here, just measure.
Measure what?
You're just going to try to use your ruler to measure the x and y components. So in my case, I estimate right here, drop a perpendicular to my axis right there, and I estimate that my x component is about 3.7. And I estimate that my y component is about 1.8. And so I would say that A is, in rectangular form, 3.7, 1.8. Just like that. Oh, it's okay if you did. But you put your ruler actually along the vector itself. You put the bottom of the ruler on the tail, and you measure out like that. You go to the head.
It's me and them that like in the beginning, like find the A.
You don't need to. You can measure it directly along, and that gives you the size, right? I mean, that ruler tells you size. Yeah. Now, it should be the case that whatever you computed for that magnitude should be really close to what you measured. Like we computed 3.68, measured 3.60. That's pretty good. Steven.
So, this is called rectangular form, but what about other one?
That's correct. So here is the rectangular form of my vector, and here is the polar form of my vector. Yes. Okay. You always start with the count. Please put your protractors on my desk if you borrowed one from me.
You know what to use.